So I just want to do a quick video on the formative that we had on 1.1 and 1.2 on Introduction to Functions and Function Notation. So the first question states on whether the following relations are functions or not, and also state its domain and range. So one of the things that we need to look for when our relation is just a set of points, so I just want to really highlight the relation here is just a set of points and not a continuous line. Okay, so sometimes I've seen some people make that mistake because maybe we're not used to it, or we're so used to seeing graphs and everything that it's connected lines or a straight line of some sort. But in this case, it's just 5 points. So we just want to kind of remember that. So in order to determine if this relation is a function, is that if the x value is repeated, then it's not a function because the x value is repeated. That means it corresponds to two different y values. So going through in here, you can see the -3, -2, 0, 2, and 6. They're all different values. They're all unique values. So we can kind of see this, or we know it's going to be a function. But since we're asked to provide the domain, as we list it out, we can see if there's going to be repeats or not. So in this case, the domain is. So when we specify a domain, or we give the domains in set notation, and set notation always use what I call the curly brace. Some of you have been using the round brace, especially sort of parentheses, especially when it's just listing certain values. So that is not set notation. Set notation is we require the curly brace. And in here we just list off the x values. So it's -3, -2, 0, 2, and 6. And since I didn't repeat anything, I know that this is a function. Then there's just a side note to know about set notation is that our elements in our set, it doesn't have to be any particular order. In this case, it just happens that our points had the x values in numerical order, and it just came out that way. But you don't have to put them in that order or any order at all. Okay. So in the range, here we're just going to list off the y values, 5, 9, 3, -8. And again, we'll have 5 again. So in a function, y values are allowed to repeat it. And we've seen functions, for example, the quadratic, where y values are repeated. And in the case of a quadratic, they're actually repeated twice for every single value except for one particular value when obviously what we're squaring is going to be 0. So in this case, we're not going to list the 5 again because in set notation, all elements are uniquely identified. So, and that's the answer to that question. So speaking of quadratics, our next relation is a quadratic. We could tell because the x in there is squared. And one thing that we just want to sort of get in our heads a little bit, and I'll accept this as an answer in a test, that if it identifies a quadratic, all quadratics are functions. We will never ever encounter a quadratic that is not a function. Why? Because for every single x value that we plug into our equation, we're always only going to get one value, one y value. We're always going to get a definitive answer. So the domain for all parabolas, for all quadratics, is XER. In other words, we could plug in any value of x and we're always going to get an answer. In the range, it's going to be YER. In this case, the parabola is pointing downwards because our a value is negative, and there's where the vertex will be, or there's our maximum value. So y is going to be less than or equal to -3. So the following functions determine f of 3, f of a, and f of w plus 2. So from what I've seen, some of the formatives, some of us are overcomplicating things. All function notation means is that we're given a function that depends on the variable x. When we say f of 3, we're just replacing x with 3 in our equation. Nothing more. Nothing more. If it requires an answer, in other words, if it could be evaluated, then we will evaluate it. If it could be simplified, then we'll simplify it. But just to start, just replace the x with a 3. And in this case, we do have a final answer of 2/3. It can't be simplified anymore. It can't be evaluated because there's already an answer. We don't need to solve for f. In this case, f is a function. It doesn't have a specific value. F of something will have a specific value, but f in itself does not have a specific value. So I've seen in some cases here people solving for f. They might be confused here because they might think that 3 is being multiplied to f, but it's not. It's just a notation. Here the brackets mean that f is a function, and we replace the value of x with 3. So f of a is just going to be 2 over a. And finally, f of w plus 2 is just going to be 2 over w plus 2. And can we simplify that any further? No, we're done. So let's go off to b, where it's a little bit more difficult here because it's actually a quadratic relation or quadratic equation that we're given. So here f of x, or f of 3, is going to be 2 times 3 quantity squared plus 3 times 3 plus 1. So notice that whatever I replace x with, I put it in brackets. So for these first two examples, not terribly important. Well, in this one, it is important because we want to see that 3 is squared. So here we got 2 times 9, and 3 times 3 is 9, and plus 1. So here we do want to go off and evaluate this because we can't get a definitive answer. So 18 plus 10, which is 28. For the next one, f of a. So again, replace x with a, and again, I'm going to put a in brackets. So in this example, it's really not necessary, but it's a good habit to get into because I don't have to remember whether it's necessary or not. Hopefully after I see this, I realize I just have to simplify this. So it's just 2a squared plus 3a plus 1. Okay. Next one is going to be a little bit more tricky, only because we have to do a lot more algebra, but not the functional notation is tricky. So here we got f of w plus 2, and this is where brackets are going to be important. Now I get 2 times w plus 2 all quantity squared plus 3 times w plus 2 plus 1. So now I have to go off and expand and simplify this. So w plus 2 quantity squared is w squared plus 4w plus 4. And then I'm going to expand the 3 times w plus 2 to get 3w plus 2. And I got plus 1 at the very end there. And then I'm going to distribute the 2, so I get 2w squared plus 8w plus 8. And I'm going to simplify the 2 plus 1 to be 3. And finally simplify everything, collect all the like terms. I get 2w squared, 8w plus 3w is 11w. And I think, oh, I made a mistake, silly me. 3 times 2 is not 2, but it's 6. So 3, this should have been 3 plus 7, because 6 plus 1 is 7. And finally, my final answer is 8 plus 7 is 15. Okay, so that's the solution to that. So really, the first one was really simple. Just replace what was in the brackets for x, and there's no evaluating or simplifying. Second one was a little bit more tricky. The last one with the mapping diagrams. So one way we need to be able to express a relation as a mapping diagram, and one of the advantages of doing that is that we could easily see if it's a function or not. So in here, I can almost see that based on what the tip I gave above, this is not going to be a function because the 3 is actually repeated. But let's do the mapping diagram, and then I'll show you how I can see from a mapping diagram whether it's a function or not. So our mapping diagram is, we need to draw 2 circles or ovals to contain our domain and range. So these are meant to be sets as well. So let's just go list it off, 3, -2, 0. And just like in set notation, we don't want to repeat values in here, so we're not going to write the 3 again. And I noticed in some of the formatives that I marked, because some of you had duplicated the 3 in here, that's why we got confused and not being able to detect that whether this was a function or not correctly. So let's write off the range, and there's all my y values, so it's 0, 8, 2, and -1. And our mapping diagram is that we're going to draw for each value in our domain what it corresponds to in our range. In other words, for each x value, point to what its y value is. So in this case, we got 3, 0, so 3 is going to point to 0, so the arrow is important to indicate the direction of the function, so to speak. So we got negative 2 points to 8, 0 points to 2. And this is how we know from a mapping diagram that this is not a function, because 3 also maps to negative 1. So in this case, because there's 2 arrows coming out of 3, we could say that this is not a function. Okay, the second one, really doing the same thing. So here's my domain, there's my range. I'm going to list it off. So immediately I can see that this is not a function because 5 is twice in my x values, negative 2 and 0. My values for a range are negative 2, 0, and 5, and then I can repeat the 5. So without the arrows, we can't tell if this is a function or not. It might look like it because there's 3 elements in my domain, 3 elements in my range, but given the full set of points, we know that it's not going to be. So let's do the arrow. So 5 maps to negative 2, and this is where I can see that it's not a function because 5 also maps to 0, negative 2 maps to 5, and 0 maps to 5 as well. So it's okay to map more than one x value to a single y value. That's not where we're looking to determine if it's a function or not. We need to look at the x or the domain side, and here 5 has 2 arrows coming out of it, so in this case we know that it's not a function.